Hi guys, welcome to Preliminary Chemistry and the water topic. And this is video number 5 looking at the polarity of water. We've started to have a little bit of a look at a couple of different places in this course about the formation of different types of chemical bonds such as ionic, covalent and metallic bonds, and also of the different types of physical bonds or intermolecular forces such as hydrogen bonds, dipole-dipole interactions, and also dispersion forces. And you may remember that in the formation of a covalent bond, one of the atoms may exert a greater force of attraction on the shared electrons than the other. This is a consequence of what we know of as electronegativity. Two oxygen atoms, for example, will, because they are the same atom, exert equal force of attraction on the shared electrons, 4 in this case, in the double bond between them. But a hydrogen sharing with a chlorine will not be the same. The chlorine has a much higher electronegativity and therefore a much greater attraction for the electrons, and hence the electrons will spend a lot more of their time over near the chlorine atom. This creates polarity. And a polar bond, which is just equivalent to a covalent bond involving shared electrons, where those electrons are more strongly attracted to one atom than another. So the result of that is we end up with a polar bond which has one atom slightly negative and one slightly positive. So in the case that I just suggested to you, a bond between hydrogen and chlorine, we have the electrons sitting closer to the chlorine atom, and therefore there would be a slight negative charge as a consequence on the chloride atom and a slight positive on the hydrogen atom. This small charge separation results in what we call a dipole, two poles, and it's a positive pole and a negative pole, just as I drew on the last slide. Polar molecules are the result of vector additions of the polar bonds between the constituent atoms, and the shape of the molecule can also affect its polarity. In order for us to analyze whether polar bonds have led to a polar molecule, we need to be very clear about the kind of shapes that we're looking at. In a situation where we have a linear molecule and a slight negative and a slight positive as a consequence of that, then we know that there's very clear polarity. This side of the molecule has a negative charge, this side of the molecule has a positive charge, and we have a very clear dipole. This is not always the case, as sometimes the way that the electrons are distributed around particularly a central atom can result in charges being cancelled out, and as a consequence there is no overall polarity despite the presence of polar bonds. So just as you go through this video, be very clear about the difference between a polar bond and a polar molecule. The most important type, or the strongest certainly, type of intermolecular forces when we're looking at water molecules are hydrogen bonds. Hydrogen bonds are created when hydrogen atoms form a covalent bond with a very highly electronegative atom. So hydrogen combined with oxygen, hydrogen combined with nitrogen, hydrogen combined with chlorine, and hydrogen combined with fluorine. Each of these forms very strongly electronegative or polar bonds because of the fact that hydrogen's electronegativity is so low and that of oxygen, nitrogen, chlorine and fluorine is so high. And so therefore the electrons tend to be closer to the non-hydrogen atom in this case, giving them all a slight negative charge and therefore slight positive charge on the hydrogen, and as a result some very high polarity exists in these bonds. Now of course this is something that's important when we're looking at what's happening between the molecules, and that's where these hydrogen bonds are coming. So the resulting covalent bonds that form between hydrogen and each of these creates this polarity. So again, if I maybe bring hydrogen and the oxygen down, because that's the one we're specifically interested in. In a hydrogen-oxygen bond, we have this difference in electronegativity creating a negative and a positive region within this bond. Of course, what then happens is that when two of these come close to one another, then we get some level of interaction because of the electrostatic attraction. So if I redraw my hydrogen-oxygen, a slight positive here and a slight negative here, and then another one was to come close, obviously oriented in the opposite direction because we know opposites attract, then the attraction between these two bonds is what is known as a hydrogen bond. Now in broad terms, it's an example of a dipole-dipole interaction because this forms a dipole here, and this forms a dipole here, and the interaction is what happens between these two. So here's one dipole, and here's another dipole. And the interactions that occur between these dipoles are called dipole-dipole interactions. And it's only when that dipole-dipole interaction specifically involves hydrogen, and specifically one of those important electronegative, highly electronegative atoms like oxygen, nitrogen, chlorine, and fluorine, that the dipole-dipole interaction is specifically labeled as a hydrogen bond. Hydrogen bonds are the strongest type of intermolecular forces, and as a result they account for the much higher melting and boiling points of water and also its ability to dissolve many substances. The easiest way to try and think about what's happening with bonding is to think about the solid. And solid water is ice. Because in the solid, something must be holding the individual molecules together. As a liquid, they slide around past one another, and obviously as a gas, as water vapor, they're independent. Their movement is independent of one another. But as a solid, all of those molecules are locked very tightly together. And because of that, we need to make sure that we're thinking about the interaction between these molecules and how they might line up in their solid state. And the way that they do that is in order to make sure that the oppositely charged ends are lining up opposite one another because of the attraction between them. So that's going to create forces which are going to impinge on the shape of the particular molecules. Hydrogen bonding is such a strong type of bonding between molecules that it raises the melting and boiling points of those hydrogen bonded molecules. It is harder for them to be separated from one another, and therefore more energy is required, and more energy is more heat. Higher melting and boiling points are the result. So when you're looking at the molecules that have a similar weight, and so therefore it's not a gravitational attraction that's holding them together, it must be something else. So with similar weights, higher melting and boiling points suggests higher or more strong bonds between them, and the best ones that we know of in this situation are the hydrogen ones. So what happens as a result is that we can then look at different molecules on the basis of these types of polar bonds and the bonding between them. So when we're looking at water being a polar molecule, it's not just because it has polar bonds. So the polar bonds are the two bonds between the hydrogen and the oxygen. There's a positive and a negative region for each bond, a negative and a positive region for this bond as well. But the difference is that these two sum together. Now the easiest way to do this is to actually draw it as a physical force, as a vector, which the physicists will probably understand a little more. If we get a point positive charge and we put it somewhere, then it will move in a direction as a result of a force that acts on it. And if I have a point positive charge, it will move away from the source of positive towards the negative. Likewise, if I put one over here, it's going to go that way as well. The consequence of adding these vectors together using a tip-to-tail method means I have a net polarity left over here. The other way of thinking about that is if I was to split this molecule in half, if I have a region that's obviously negative and a region that's obviously positive, then I have a negative region positive region, that equates to a dipole, and therefore I have a polar molecule. Now what about carbon dioxide? Let's quickly look at that one. The thing with carbon dioxide is that it's a linear molecule. Carbon needs 4 covalent bonds and oxygen needs 2. So therefore the carbon will form 2 double bonds between 2 separate oxygen atoms. Now there is a charge separation here. The oxygen is more electronegative, so it will attract the electrons more. They'll be more towards this end of the oxygen and also more towards this end where the oxygen is. So it'll be a negative and a positive here. But if we do our point positive charge, then again it's going to move in this direction, or it's going to move in this direction. And those of you who know about vector addition means that if we put 1 here and then our tip to tail method brings us right back to the same place, then our resultant is 0. And that means there's no polarity. No polarity. So carbon dioxide is one of these molecules that has polar bonds, but is not a polar molecule. Thanks for watching.